Now, we will start section 2.2, which is tangent planes and normal lines to surfaces. First, let us take up tangent planes. Now, let us take a surface like this. We know that at point P, you have a unique direction, that is the normal to the surface at point P. The normal direction can be obtained by grad phi. Now, once you evaluate that at point P, you get this tangent. The general grad phi gives you the normal at any point, but if you want to find the normal vector at this point in particular, you have to plug in the coordinates of P. Let that constant vector be ai plus bj plus ck. Now, even though there is only one normal line you can draw at point P, there are infinite tangents. For example, if you take this board itself, take this point for example, this is a tangent to this point. Any line on this plane passing through this point is a tangent, this is a tangent. So, those infinite tangents form a plane, that is called the tangent plane. Now, here there are infinite tangents you can draw at point P to the surface. Those infinite tangents form a plane, that plane is called tangent plane. Now, how do we find this one? Let us see. This is what we do. We take any arbitrary point on this tangent plane, let it be capital X. Now, you can always find Px, right? Px is this vector, right? You subtract the respective components and get this vector, right? X minus x naught I plus y minus y naught j plus x minus z minus z naught times k. Now, you can see that this is on the tangent plane, this is the normal direction, therefore, they are mutually perpendicular, right. So, they are mutually perpendicular, therefore, the dot product is equal to 0. Now, this is vector Px. If this is the vector grad phi evaluated at P, you can plug in that constant vector. Now, take the dot product. So, A goes hand in hand with this one, B goes hand in hand with this, and C goes hand in hand with this, which is the sum of those is equal to 0. Now, this is the equation of the tangent plane. Always, no matter what the surface is, this is what you need to do. You have to find this unique direction, then consider the tangent plane and pick an arbitrary point x, get the vector Px. Now, you have this vector, they are mutually perpendicular, therefore, you perform the dot product. The dot product is always 0. From that, as we saw towards the end of the introduction, you can always come up with a relationship like this. This relationship is in fact the equation to the tangent plane. Now, we will start the next one, the normal line. Here again you can determine this unique direction at P, that is the normal vector drawn at point P. So, you find grad phi. Grad phi just gives you the vector at any point. So, to find the normal vector at point P in particular, you plug in the coordinates of point P to grad phi, then you get a constant vector like this. Now, we need to find the normal line. There is only one unique line, there is only one line, that normal direction is unique. You have only one line here. So, you pick any arbitrary point x, capital X. Now, as in the previous case, you find vector Px, you can find it, then it is here vector Px and grad phi evaluated at P are parallel to each other. So, you can write this statement. Now, this is Px, you can easily obtain that one. Grad phi evaluated at P is in this form. Now, since they are parallel, what do we know? Their corresponding ratios should be equal. So, x minus x naught over A, y minus y naught over B, z minus z naught over C are all equal. Now, you can see that this is the equation of a line, and in fact, this is the normal line, your equation of the normal line drawn at P. Right. Now, we will take up an example. One example is sufficient because all the other tangent planes and normal lines are found in the same way. Right. So, find the tangent plane and the normal line drawn to this surface at 2, 1, 1. Now, I mean, here we do not need to sketch this surface to find the equation of the tangent plane and the normal line. However, just for the sake of curiosity, let us sketch it. You know, you take these two, Z to the other side, and you know that the left hand side is always greater than or equal to 0. This cannot be non-negative. It's either 0 or positive. So, therefore, right hand side follows the same suit. So, 4 plus Z greater than or equal to 0. So, it yields Z is greater than or equal to minus 4. So, this diagram cannot go beyond minus 4. I forgot one thing just to mark that point. And on the other hand, at Z is equal to minus 4 here, right. If you plug in minus 4 there, you get x squared plus y squared is equal to 0. When two squares are equal to 0, the only possibility is that each one should be equal to 0, right, because if something contributes some positive value, the other one cannot contribute a negative value to make the sum to 0. Therefore, both should be zeros. Therefore, x is equal to 0, y is equal to 0. So, this is the point, this is the vertex of this diagram. After that, on this plane Z is equal to 0. If you plug in 0 for this one, you get x squared plus y squared is equal to 4. So, on xy plane it is a circle of radius 2 centered at the origin, and always you can see that when Z goes up, x squared plus y squared goes, the sum of x squared plus y squared goes up, right, but not in a linear way. You have to increase Z much more to get a same increment here. For example, when Z is minus 4, you get a point. When Z is minus 3, you get a circle of radius 1. Just after increment of one value, 1 unit, you get a circle of radius 1. But after that, you have to increase it by 3 units to get a circle of radius 2, because from minus 3 to 0, you have to go 3 units up to get an increment of 1 unit in the radius here. So, it has this shape. So, it is like a paraboloid, it is a paraboloid. Always you know, you have the shape of the paraboloid once two variables are squared and the other one is not. Then in fact, the variable which was not squared stays as the axis, like Z is the axis of this paraboloid. We discussed those things in section 1. Therefore, it is not necessary to go through all those details. Now, 2, 1, 1 is somewhere here, because this is the point of our interest. We need to find the tangent plane and the normal line drawn to this paraboloid at this point. So, now let us get into the problem. Now, phi can be taken, you take all the constants and variables to one side, this is phi. Now, you find grad phi. It is a simple exercise. Once you deal with these partial fractions, you will end up with this one. Now, this is just gives you the general normal vector. Now, if you want to find the vector at point P, you evaluate the vector at these points, at 2, 1, 1. So, you plug in those coordinates there and you will end up with this result. So, this is the normal vector drawn at point P. Now, we will take one after the other. First, let us take the tangent plane. Now, you need to have this one at your disposal, right. Now, tangent plane. Now, this is the portion of the surface, this right. Now, let P is somewhere here. This is the normal vector. Now, this is the tangent plane. X is on this plane. X is any arbitrary point on this plane. with coordinates x, y and z. Now, P is here, so you figure out vector Px, it is this one, subtract respective coordinates and get it. After that, you can observe the fact that Px, the vector Px is on the tangent plane, grad phi evaluated at P is a normal vector. So, those two are mutually perpendicular. Now, because of that you can take the dot product and you can make it equal to 0. Now, this is vector Px, we have already found it. This is vector grad phi evaluated at P. So, you can take this dot this is equal to 0. Now, you perform the dot product. It is a simple exercise to understand. You straightforward calculations yield this result. Now, simplify, put keep all the variables in the left hand side, get the constants to the other side. So, you have 4x plus 2y minus z in the left hand side. Here you get minus 8, minus 2 and plus 1, altogether minus 9, you bring it to the other side. So, it is plus 9. So, this is the equation of the tangent plane. Right. Now, in the same fashion, again this is a portion of the surface, this is the point P, you have grad phi evaluated at point P, you know that, and we need to find the normal line. Normal line is also on the same vector, right. So, you take any arbitrary point x, any variable point, with coordinates x, y and z. Now, you find vector Px, it is this one. Subtracting the respective coordinates, you can find the vector. Now, grad phi evaluated at P, we have already found it. Now, these two are parallel to each other, therefore, vector Px is parallel to grad phi evaluated at P. Why? Because grad phi is always the normal vector. Now, when two vectors are parallel to each other, this is vector Px, this is vector grad phi evaluated at P, their respective components should maintain the same ratio. Therefore, x minus 2 divided by 4 is equal to y minus 1 divided by 2 like this, and z minus 1 divided by minus 1. So, this is the equation of a straight line. In fact, this is the equation of this normal line drawn to the surface at point P. So, this is quite straightforward. No matter what surface you get, right, no matter which point you have on the surface, it is a straightforward calculation to do it. Always find grad phi, right, like I have done here, grad phi. Then evaluate grad phi at that point to the given point, like I have done here. After that, have a little clear diagram and then indicate the vectors and what you require, what is required. After that, come up with a relationship. Either those two are parallel or those two are mutually perpendicular. Based on that, you come up with a relationship. That relationship gives you the equation of that line or the plane. Okay. Thank you.